You know, the interesting thing is, or the fascinating thing about robotics is that it's highly interdisciplinary, and many of the things that I've done in my scientific career somehow can now be lumped into well, the HBP, the Human Brain Project, which, as you know, and I mean, Felix gave this fantastic introduction yesterday evening, is the leading ICT project in Europe. I mean, there's another flagship, but you hardly hear anything about it. So HBP is really at the center of Brussels' attention. Okay, so but this is now about neurorobotics. It's a large field. It has grown over the last 10 years a lot. I give you a short introduction in the beginning about the history and the basis and what we are going to do and have already done in the HBP for the last 2 years. 2.5 years now. Actually, I mean, I was involved in defining the flagship funding scheme with the European Commission, and all this started already back in 2008. Then we had, a number of political circles and political, commissions and people to convince that this is indeed a very suitable funding scheme. And the purpose was at the beginning already that we were trying to put Europe on the landscape of big ICT projects, big scientific projects again, and I think we've managed that. I hope to convince you, and maybe I'm preaching maybe to the converted, that you are of the same opinion. Felix certainly is. If there are any doubts, you can ask me or him or anyone, or David in particular. He's been he's been on board since the very beginning. Okay, so let's talk about neurorobotics. I have 80 slides, so don't be fooled by that. I'll run you through the slides, give this panorama. Obviously, we can only touch on the neurorobotics in the next hour. You can also interrupt me if you want, but we have half an hour of discussion afterwards, so there should be ample time. And then, of course, we can give you these slides if you're interested, and we can have a discussion also in the afternoon. Okay, so this is the outline. I will first, as I said, give you a short introduction, then what we are doing at the moment, or what is happening at the moment in neurorobotics. I will then introduce you to SP10, the sub-project 10 of HBP, which is neurorobotics. By the way, neurorobotics, and I'll come to that in the neurorobotics platform sub-chapter of the talk, it's a platform, so we will make software available for everyone, and I mean really for everyone who's interested around the globe. The platform is already partly available inside the HBP. We are beta testing it, if you will, and so everybody can use it, and I really like to encourage you to use it. We have only very few code jammers here, I think, at the moment, because they're all code jamming, right? Yeah, so you're more than welcome to try it out, and then get involved is my final chapter. Okay, so introduction to what is neurorobotics. Well, it's not really an emerging, it is already an interdisciplinary field of research at the intersection of, in silico, neuroscience and robotics, right? So it's about building robots with brains. Embedded brain, so you have this robot and you have a small computer or whatever inside that acts like a brain, hopefully very close to what Felix outlined yesterday. We are drawing heavily on the resources that are provided by the brain simulation people, i.e. by him and a few others, but I mean, he is the maître de plaisir of that sub-project, so yeah, he is. He has to, shake his head, but as a matter of fact, he's the one to talk to. And clearly, these embedded computers should, as far as possible, mimic the structure and the function of the nervous system of creatures. The development basis, or the basis for the development is, and this is something that I'll come back to, the moment, of course, I cannot really go into much detail, is biologically accurate models, as far as that's possible, of brains and bodies, right? And the approach is we would like to, and we will, build these robots, both in the real world, but also in the virtual world. I had a long discussion with Henry before we actually put in the proposal for the HBP, whether we should do it all in the computer, in the virtual world, or in the real world. And then we decided that, following his advice, we would start in the virtual world, but of course we would not neglect the real world. So we are building real bodies with real computers. But at the same time, we are doing it all in the virtual world. And we try to calibrate the two so that we can simulate stuff. And once we are happy with the behavior, happy with the entire design, we can then readily or in a straightforward manner design physical robots, maybe with 3D printers and stuff like that. Right? So the approach is we let these robots live in a habitat, right? We observe them, we put in a simulated brain, and the idea is once we get a behavior that matches the behavior in the real world, we can then measure anything inside the virtual robot. And you may remember from Felix's talk yesterday that, with these patch clamps, people can only, measure at certain points of a neuron. Once we have a model that is fine-grained enough and that has enough neurons and shows off a rich behavior, we can, in principle, put an electrode, a virtual electrode, everywhere. So we can measure things that you would never be able to measure in a real creature, maybe not with reasonable effort. And that's a major advantage if we have this whole thing running in a computer. But there are also practical reasons. Why should we link brains to robots? Well, clearly, in biological robots, I'm hesitant to call these robots, but creatures. The algorithms are embedded in hardware. Everything operates in real time, clearly. Right? We don't have, it's all real time, because otherwise these creatures wouldn't be able to live. The brain is massively parallel by construction. The decomposition into parallel tasks is obvious. It's self-organized, it evolves. And then clearly, as you can see, the architecture is scalable from 10,000 or even 5 neurons to Einstein's brain, 85 billion neurons. Your brain maybe has even more neurons. So it's highly scalable, and this is something that is obviously very attractive. Right? The performance is robust, and the energy consumption is also very low. If you recall that basically we have, as some people say, we have a petaflop computer consuming only 20 watts. So that calls for a neurorobotics approach. So what are the goals, at least the ones for neurorobotics research that we have formulated? Well, clearly in robotics, the robotics perspective is that we want to apply findings from neuroscience directly, and therefore the HBP is really the ideal project. Apply findings from neuroscience to robotics, overcome the limitations, and there are many, of standard control architectures that are in use in robots today, and use neuromorphic hardware for the control tasks. So the neuromorphic hardware means Spinnaker, I'll come to that in a second, but also maybe at a later stage, the hardware from Karlsruhe that Karl-Heinz Meyer will present to you tomorrow in the morning. Then, from a neuroscience perspective, as I tried to outline a few moments ago, to use the robots as a tool for testing hypotheses. Right? So instead of, in a remote future, we may be able to replace animal experiments with robot experiments, because we know that the robots would behave in exactly the same way as the animal under test. Right? And as I said before, the full observability of everything in the brain model is also, from our point of view, a very attractive feature. In particular, if you consider that the robot can interact with a real environment at any time. It has to interact with the real environment, because otherwise it would be of no use, right? So the interaction with the realistic environment is a key feature, which we think is also very attractive for neuroscientists to explore when using these robots. And if we have realistic environment models, like for example this room, right, with all its features, texture, lighting, acoustics, everything, then we can really model things completely in the computer. We can go completely virtual. And then there's another very important aspect. I mean, you've all heard about the deep learning stuff, and I'll also come to this in a moment. So learning is a very important individual aspect that we pay a lot of attention to. So we would like to capitalize on the fact that we have this robotic embodiment to study and to develop the neurobiological models. And then, of course, the other question is, once we have this robot, what can it do that makes sense and that is useful, right? I mean, we can have robots that, just run around like in a maze, but who would be interested? Who would buy a robot like this? I mean, people wouldn't buy a robot just for fun. They want a robot to do useful things. But how do you train the robot to do something useful? It's a very open question, at least from our perspective. Okay, let us briefly look at the history of neurobotics, right? So it started already actually in 1948, not far from here in Bristol. I have a short video showing the Sir Walter's tortoises, which were simple robotic platforms. Then, it went on, but with very limited resources. And then in 1987, the Japanese started a project called the Remote Brain Robot. And alongside with this, there was the feedback error learning neural network, which is a hierarchical neural network model, which was more powerful in many ways than what we had before. So we can call this a milestone. And then Kretschmer, Edelman, Santa Fe Institute started the so-called Darwin series of robots. There's a book by Kretschmer, Neuromorphic and Brain-Based Robots, if you're interested. This is from 2011. This robot that you see, the robot Nomad, I think is from the early 2000s. Right, so these are the first major steps, but the first one is so interesting because basically I have this short video.
In a simple villa on the outskirts of Bristol lives Dr. Gray Walter, a neurologist, who makes robots as a hobby. They are small and he doesn't dress them up to look like men. He calls them tortoises. And so cunningly have their insides been designed that they respond to the stimuli of light and touch in a completely lifelike manner.
Lifelike manner.
This model is named Elsie, and she sees out of a photoelectric cell which rotates above her body. When light strikes the cell, driving and steering mechanism sends her hurrying towards it. But if she brushes against any object in her path, contacts are operated that turn the steering away, and so automatically she takes avoiding action. Mrs. Walter's pet is Elmer, Elsie's brother, in the darker vest. He works in exactly the same way.
fascinating is that
Dr. Walter says that his electronic toys work exactly as though they have a simple two-cell nervous system, and that with more cells they will be able to do many more tricks. Already Elsie has one up on Elmer. When her batteries begin to fail, she automatically runs home to her kennel for charging up, and in consequence can live a much gayer life.
okay, so this was 1955, and there is a professor at Essex, former professor at Essex University, Owen Holland, who reproduces these as a hobby, and here you can see an LC with a transparent body. So that was the state 60 years ago, right? And I mean, if we want to be self-critical, we haven't achieved much more. But that's not quite true. But it's really impressive to see what he was able to do back then with a few, with a photocell and a few electron tubes. And the state of technology then. Okay, so in 2003 then we went on, Floriano and other people did some benchmarking studies on active vision. So that means how do creatures react to visual stimuli. And today, of course, we have large-scale brain stimulation, neuromorphic hardware, biomimetic robotics, and so on. If you look at the field in terms of publications, in 2000, we had like 50 per year in this field, and now it's over 700. So it's really something that's growing. Let me give you a few examples of current research in neurorobotics. Well, first and foremost, our own stuff at TUM, which is, I think, already quite impressive. We are using, so this is a mobile robot with 2 cameras, onboard batteries, of course, and an 864 core spinnaker board, right? Of course, courtesy of Dave. Actually, we are not using all of them, to be honest with you, but so there's more potential for you to try this out. What can we do? Huh?
Give them back.
I give them back, yeah, I give them back partly. So at least partly. So half of the board you can have back because we're only using half of it. So well, I mean, we have the system. It's, as I said, equipped with two cameras that are basically silicon retinas. So these are cameras that only react to changes. The information is fed into the spinnaker board. And we can do a number of very interesting things, right? For example, trajectory stabilization, so that when this robot pursues a certain goal, it does that in a very, biorealistic way, stable. It can track stimuli like LC 50 years, 60 years ago, but of course in a much better way. And there is some potential for learning by demonstration. So this is one of our systems. We are going to build many more like these in the project, and with the help of David. And yeah, you're more than welcome to help us and to explore this and to use this as a platform for your own hypothesis. So if you have anything that you would like tested in a real environment, come to us and we'll be more than happy to help you. But there are, of course, others. For example, the work in particular by Auke Eisbert from EPFL, right? The observation is that animals are able to move seamlessly in their environment, like the salamander here. And it looks very natural, of course, because it's a creature. But if you look at these creatures in a little more detail, then you see that even though this looks intelligent, it's actually a very simple motion and a very simple behavior pattern that is generated by so-called central pattern generators in the spine, on the spinal cord, and it makes it possible for them to really navigate very, intelligently in their natural habitat, right? So this, having observed this, I mean, one could have the idea that that you imitate this, that you use this as an inspiration for a robot, and this is what Auke at EPFL did. So he built this salamander based on his observations with the CPGs, right? And this system down here is a modular biomimetic robot with 4 legs and an actuated spine, based, as I said, on this theory of CPGs. And this robot is actually capable of walking, salamander-like walking, and swimming. So this is could also be a very good tool. And iCub would certainly also be happy to work with you for robotics and for neuroscience. So here's a video. So here you can see this walk, and then once it gets afloat, it starts swimming in a very natural way. I mean, it's little you can. I mean, if you looked at it from a few meters further away, it would be difficult to tell the difference between this one and the real one, right? As long as it's in water, and when it gets out of the water, it starts walking again. So I find this very impressive. But it's the result of 20 years of work. And of course, then the next step would be, and we are working here with Professor Nakamura from the University of Tokyo to do a similar thing, start working on the human body and model the human body with all the muscles, all the tendons, all the bones, which he did. And the resulting model, unfortunately, we didn't get, I mean, he has lots of videos, but I wanted a particular one to present to you, but unfortunately, we couldn't get it. Suffice it to say that this is probably the most detailed model of the human body available today. And it has 155 degrees of freedom, which I think speaks for itself. And they are adding a neuromuscular model to it, and the resulting behavior is it's very human-like, very impressive. So if you're interested in that, you're also more than welcome to talk to us. But, so I mean, everybody knows that, right? And you can try it out. Well, I think put this off. You can try it out yourself. Sit on a chair and use a hammer or maybe you use your neighbor and try out with a hammer. And then the question is, how does that work? At Tokyo, they developed a model for this. And if you watch that video, it's really very, very natural. So that's another example of neurorobotics, if you will. And then, of course, there's this large field of cognitive developmental robotics. So the question here is, how do humans develop, and what can we learn for developing robots? Right? Because there's certainly a reason, or how shall I say, an effect that you can expect from growth, right? Because, I mean, when you have a fetal being up to the, then a toddler and an adult, all the parameters of the body change dramatically, but somehow things are controlled in a very goal-oriented fashion. So what happens in the meantime? How do we do that? What can we learn from it? And again, the people at the University of Tokyo have done very impressive work. So they have looked at, this is in particular Kuniyoshi, Professor Kuniyoshi. They have looked at individual stages of fetal development. And they have developed models with spiking neurons. And the take-home message from that work is that you really need, or what they claim is that you really need lots and lots and lots of sensors on the body, or measuring points, if you will, on the skin, and then you can do a lot more than if you have an isolated network which has no contact and no interaction, no sensing interaction with the real environment. Fortunately, we are almost we are definitely too late. So here's an example of a learning baby. So this is Kuniyoshi's baby, right? And there are, you can't see this, but it has ears, eyes, and lots of sensors around the skin. And you start with an empty network, but then after a few minutes, when you touch it and there are stimuli, optical stimuli, and a bit of noise, it starts reacting. And again, if you're interested in this, I can only refer you to Kuniyoshi. Very interesting work, also a very good example of neurorobotics. Okay, so it's SP10, our own sub-project in the Human Brain Project. We started, well, I mean, as you know, with a motivation that we wanted to build more intelligent robots, like many other people, right? So we are in the mainstream of robotics development, and here are the skills that we would like to see these robots to have in the future. So perception, clearly out of the box navigation. You unpack the robot, you buy a robot, you unpack it, you want it to be able to navigate in your flat immediately. Of course, that's extremely difficult. Humans with their brains, need many, many years to arrive at the stage where you can really navigate in a hallway, in any hallway in the world, right? If you try to teach a robot what a hallway is, that's already quite difficult. So maybe you can train it to navigate in this particular hallway, but then you have that hallway and the whole thing fails. So that's a real challenge. For example, right? Working with others, goal-oriented behavior, so I wanted to do something that I wanted to do, decision-making, and up to the maybe one day level of consciousness. And then, of course, you also want these to be fault-tolerant, have a low energy consumption, be lightweight, robust, safe, cheap. So anything that you can't get from a human, you want from these robots. And the question is, where do we start, right? So this is the SP10 in. I come back to this question of where do we start? Where did we start? Basically, in a moment. This is the embedding or the positioning of the SP10 neurorobotics in the HBP. So this is neurorobotics. We have close ties, of course, to neuromorphic computing, brain simulation, cognitive architectures, maybe a little less tight ties with strategic data and neuroinformatics. But it's interesting to see, if you work in a project like this, who you can profit from, who you work with, that you would never have expected to work with in the beginning. Right? Okay, so this is actually the first robot that we built together in a European project called Echar Robot. There is a video. This was 2009. A video on YouTube that you should watch. It's quite popular still, and you can see we built a robot that is very similar in dynamics and design to the human skeleton. And the working hypothesis was, and still is, that if we have similar dynamics in a body, or a body with similar dynamics as the human body, we should be able, or it's the only way of really achieving human-like behavior, human-like intelligence. That's the hypothesis of embodiment, right? And once we have an embodied robot, then we can maybe really achieve at the point where we have intelligent perception, cognition, and can really make a connection with brain research. So our mission is that we want to contribute to theory, right? I once said we want to develop a Hilbert program, in all modesty, towards the ultimate cognitive robot. But on the practical side, we would also like to design modular brains for modular bodies. Because clearly you do not always want a full humanoid robot. Right? I mean, would it make sense to build a humanoid robot to operate your vacuum cleaner? Or might it be better to build an intelligent vacuum cleaner in the first place? Probably the second option would be the choice. But then what parts of the brain would be useful to integrate into an intelligent vacuum cleaner? Maybe a skill for navigation would be useful, but also an audition module, so that when you come in and say, stop, or clean now, start cleaning now, the robot would listen to you and do what you want. Right? So That's the question. Yeah, so the purpose is, and I'll come closer to this platform aspect, the purpose is to really build an appropriate tool chain for connecting brains to robots, and this is what we are doing. So this is the tool chain. We first want to define a system that we want to control, so a body. It could be a real body, or it could be a virtual body, like, for example, this mouse, which is our SP10 virtual mouse. Then we would define the desired level of simulation granularity, pick the model, instrument and align it, so determine the signals and actuators and the motors in the body that we want to connect with our simulated brain. And then we would execute the experiment, right? So it could be a scientific experiment, but it could also be, as I said, something that would be useful in your household. An example of this is actually our first, this was our first real Neurorobot, right? It was the ball balancer, very simple robot, but it has everything we need, right? It has a dynamic vision sensor, like the one I showed you on this mobile robot with the spinnaker board, a ball, 2 actuators, so it's only 2 degrees of freedom, very simple. But already a spinnaker-based controller, a spinnaker board with 4 chips, of which we used only 1. So there seems to be, some mismatch, but it's always good to have more computing power than you need. And then it's a Zurich sensor, yeah. Yeah. Like on the other one, it's a silicon retina. So it's actually from the Institute of Neuroinformatics, which is a little bit ironic because it's led by Rodney Douglas, who's not a great supporter of the HBP, to say the least. But we're using the... Huh? We cooperate. Yeah, which is a positive development. So anyway, we were using this together. I mean, this was basically Conrad's work, Professor Conrad's work at TUM. And what you don't see here, so this is the hardware. What you don't see here is, of course, the model that we're using to control it, and this is again this blue brain column that Felix presented to you yesterday. We simplified this a lot. The advantage of this cortical column is, of course, that for the computer scientist it's ideal because you can discern very easily all the levels of processing. Right? You have an input layer, and then you have an output layer, and everything in between, and it's all clearly discernible. So it's very good for a computer scientist. Very compatible with our view, right? You can't see it on this projector, but here, when we simplify this, and I really can't go into the detail here, but if we simplify this and program it in an appropriate way with, for example, with Nest, the simulator that was mentioned by Felix yesterday as well, then we get a model which runs which can run on a PC, while this needs a supercomputer, or it can run on a supercomputer in an extremely fast way. And then what we did was we simulated this, right? So the task is really to balance this ball in the middle, and then here is a video of the machine. And as you can see, it learns, or it gets trained in the model, in the simulation. Then we transfer this program to the actual machine, and after a few tries, it balances. Well, of course, this runs because it's a video, but it also runs in reality, like this, so we can show you. Okay, let me now come to the platform. What are we providing to you? What is our vision? The vision is we will provide the brain models with a body, or we will give the models a body. And the most important metaphor is the closed loop system. So we have an input. So the system lives in an environment. As I said before, it could be a virtual environment, it could be a real environment, it could be this room. Right? So we model this room, right? The system has sensors, the robot system has sensors that pick up the information from this room, It has a certain goal, so it should have a goal-oriented, or should develop a goal-oriented behavior, picks up the signals in this room, processes them in a certain way in the brain, in the simulated brain, on the Spinnaker system, for example, and then it translates these stimuli into action. In other words, it drives around, it flies around, it moves around in this room, and that, of course, again changes the perception, so you have this closed loop, like we observe in almost every creature that has senses, a cognition unit, if you will, and actuators. Right? So this is our vision. We want to build these closed loop systems. The first one you've just seen, there's a camera, there are motors, there's the Spinnaker system in between. But of course we would like to expand on this, and this is the purpose of the Neurorobotics platform. Right? We have, as I said, we want a simulated physical environment first. We provide a simulated physical environment first, which has the advantage that everybody can use it, because you don't need any hardware for this. You can use your phone and experiment on your phone. And of course, this should be all in state-of-the-art, or cast in state-of-the-art software. So the features of the Neurorobotics platform are: we have this user interface, which is web-based, so it runs in the browser, basically. But it's completely scalable, so it can not only run on the browser, it can also run in a cave, for example, in a big visualization room, right? We provide the closed-loop engine, so the director, if you will, that directs the interaction between the simulators for the room, or the environment, the simulators for the robot, and the visualization engines. And of course, we will provide a lot of examples for users, for you, if you want to use it. Right? So we can design environments, we can design robots, we can put different robots in different environments, and we can try out, in principle, everything. So the components of this platform are like this. So we have designers, so environment designer, robot designer, brain interface and body integrators, and then the experiment designer, for example. So if you're a neuroscientist and you may want to, have an artificial mouse running in a maze, then you would be interested in the experiment designer. An industrial robots engineer might not want to use this, but of course nobody is forced to use it. Then we have the closed-loop engine, the world simulation or the world simulator, and then a little bit of infrastructure which remains hidden from the user. And we have different kinds of viewers. So it could be, as I said, it could be any web browser, but it can also be high-fidelity simulation viewers. We are using, for example, the video wall in Geneva as an output device. We have a number of bodies already available. So we have a model of the iCub, which is the result of a long tradition of European projects. A lot of money has been invested into the development of the iCub, which is a robot baby. It's about this high. The development must have been around 2004 or 5. Then we have the HBP Mouse. This is a model which is not, we have better models or better visualizations of the model. We have Lauron from KIT, Karlsruhe Institute of Technology, which is a hexapod robot already in its 5th generation. That development started in the late 80s. And of course we have Roboy, the robot that we have developed together with the University of Zurich, Rob Pfeiffer, and his team. Okay, let me give you a short overview of the HBP mouse, because this is something that is already available. So we have developed this mouse body, and we are at the moment developing a much more detailed one. This is a rather rough one, and a first 200,000 neuron mouse brain model, which was basically developed by the brain simulation people, Felix and his crew, but we are using it. actually quite successfully. Here you have an image of the mouse, right? This is just the body. As I said, it's a relatively rough model. And this is the mouse, just the body without the brain, so it does nothing, right? It just falls on the floor, but you can see that it's elastic and it has a very rather natural appearance already. But as I said, we are working on much better models at the moment. So this was 2 years ago. And but from my point of view, the most important thing is really that we have managed to match already touch, so the whiskers and part of the nose here, and in particular also the limbs and the legs, to this simulated brain. So we have made this connection, and on the next slide you can see this is the mouse falling, and here you can see the activity levels in the simulated brain when the mouse falls, and you can even see when you touch it here, right, to things to light up in the respective part of the mouse cortex. So I very much like this because it shows you that we've done it in the simulation. You can touch it, you can see the reaction in the brain. I mean, you can say this is totally unrealistic, but it isn't, because it all this is to some extent calibrated, and it's based to a large extent on real data from the Allen Brain Institute. So it's already quite realistic. But of course, I mean, everybody is invited to help us turn it into an even more realistic simulation. So some technical details. Of course, we're using as much available software as possible. So we see ourselves more in the role of system integrators and simulation engine integrators, rather than we develop everything from scratch. That would be totally unreasonable. There are lots of very good simulators out there which are open source and which we can use. But there's still, believe me, I mean, there's still a lot of work to be done just to integrate these tools so that you can make use of them in a sensible way, right? And then we do all the, we have to do all the gluing between these tools. For example, develop transfer functions, or first of all, even develop the concept of transfer functions with which we glue together, the nest simulation and the sensors and the actuators of the robots, because nest in itself is just a simulator. How do you connect the simulator? And then how do you connect the simulator to work in real time, or at least in simulated real time, with the body? That's the stuff, the kind of stuff that we've been working on. But now it is almost ready for release, right? So here you have for example, an overview of the closed loop engine as one of these things that glue together the simulators. We're using Nest for the brain. We're using a gazebo for the simulation of the robot and the environment, and we're using. We have to use ROS with all its deficiencies for running the robot system. We can use that, as I said, in the simulation, but also in the real world. So this is basically the data flow, maybe not so interesting, but we started out with a very simple example. Brighton Berg vehicles, probably the simplest robot you can think of. This has 4 wheels. It's not really very humanoid. It has 4 wheels, has 8 neurons, right? And the purpose, of course, is like with LC, phototaxis, follow a stimulus, right? So we have this room. Let me show you this video briefly, but before we started, explain this to you. So we have simulated this room with 2 monitors that change their color, for example. So this is the robot, the Brighton Berg vehicle, and here you can see the simulated spike trains of these 8 neurons. This is a rather coarse, rather rough simulation. We can do much better now. This was done roughly a year ago, but basically it shows you the whole environment. So we have this room. The robot, roams around, looks for. So we change the color. and then it looks for red or it looks for blue. And down here you can see 8 tracks of the spike trains, or the recordings of the spike trains of these 8 neurons. And then, of course, you're free to change whatever you want, right? So you can now, not then, but now you can change everything, every parameter in real time. You just change a parameter, and you can then observe the change in the behavior of the robot. So this was a year ago. Now we also have, for example, the iCub standing in that room, and this is about the achievements until last September. So you can, here you have your, it's a pity that we don't have the CodeJam people here, but you can, in Python, you can change everything. And this experiment was basically active vision on an iCub. You can change it, you can observe the eyes, you can see what it sees, everything. It's all open because it's all in simulation. You can look at everything, down to to every neuron. Here, for example, you have a maze experiment with the mouse, right? With this, here you have a Loron experiment. So everything is there, and it will also be available on the web. So you can see it's already functioning. You can use it on your iPhone as well as on the video wall. Here, this is the video wall still in Lausanne, right? Okay, I think you get the message. Let me move on. I have a number, but I skip these. We can discuss them. So, what is the future? Well, the future is, of course, first and foremost the body development. We started with Echar Robot back in 2009. We're now working with Roboy and the follow-up robots. We are firm believers in this theory of embodiment, right? So the morphology of the body shapes the interaction with the environment. A lot of computation can be offloaded from the brain if you use the right body, right? So if it has the right flexibility, the right plasticity, and so on, then there's a lot of stuff that you don't have to do in the brain because it's already done by the body, because the body adapts to the environment without any computation, right? Some people call this morphological computation. We also want to we'll continue working on these bodies because we think that highly realistic input, generating highly realistic data from these bodies that have these human-like dynamics, makes it much easier for you and for us, of course, to simulate, to arrive at better simulations, much more realistic simulations, right? We are working on artificial muscles. That this arm, by the way, is a really very unique and powerful design. We've been working on this for many years. It has a spherical joint up here, like the shoulder. It's soft. It's back drivable. It's safe because it's it doesn't have it's soft, so it won't hurt you. Unlike a industrial robot that could even kill you, this one can't kill you, right? You wouldn't expect a baby face like this to kill you, right? So it all fits together. We also have the models, right? For example, this one was our first model back in 2009, right? The Echar Robot model. So it was not easy to develop simulators for these, for these mechanisms because it's all highly non-linear. Everything else that was available at the time was for linear kinematics, but with these tendons in all places, it's really difficult. It was really difficult. But you see, this thing it looks quite realistic, and it actually was quite realistic. We then went on to build the arm that I just mentioned. So this is this design, right? It's very similar to the human arm. And it also the motion is very smooth. Took us 2 PhD dissertations. 2 PhD students worked on this for 4 years to design the controllers. So a lot of work has gone into this, even though it looks very natural. But that's, by the way, also a big problem in robotics, right? The more natural it looks, the less people understand, so what's this all about, right? I can do this, so it must be easy, exactly, right? Yeah, and then this all went into the development of Roboy, right? Here's a video of Roboy. Rolf, I don't know, is this video playing? Yeah, maybe I can.
In the joints, right? But humans obviously don't have motors in the
TED
joints,
Talk.
but we have muscles and tendons that are pulled over the joints. And what we try to do in Roboy is not only replicate the superficial appearance of a human being, but the inner structure with joints, bones, muscles, makes sense. Most robots have motors in the joints, right? But humans obviously don't have motors in the joints, but we have muscles and tendons that are pulled over the joints. And what we try to do in Roboy is not only replicate the superficial appearance of a human being, but the inner structure with joints, bones, muscles, and tendons. So maybe we can briefly have a look. So hi, Roboy.
Of course, it doesn't answer because this is not a video, this is real.
Okay, so now what
It should have said hi.
Can we have a close-up on the shoulder?
Hi, Roboy. It's a pleasure to meet you.
Yeah, this is again this arm, right, that I mentioned to you.
Ah,
Okay,
very good.
unfortunately we
So
don't have the
maybe-
time, so we have to stop this here. But it's quite funny to watch Rolf to explain the Roboy, and it's been a major success, right? I mean, it's been around the world. Everybody likes it. There was a show in Zurich where people were actually lining up, 200 people, even paying for seeing Roboy, right? Even though it doesn't do much, but there seems to be a tendency that people like these artificial creatures. So then we went on, and in the next European project called Neurorobotics, we developed a kit, a modular design with which we can build all kinds of bodies, right? For example, this one, I'll come to this in a second. So this is a very, it looks like a very, it's actually a very simple mechanism. It has only 1 degree of freedom, but you can change the elasticity of the thing. You can change basically every parameter, and you can do interesting experiments with this. For example, you can use it even as a catapult, right? So it's so soft, and you can throw a ball. You can build a thing like this, a quadruped, which of course is too heavy to walk, but at least it can show off the different sorts of gaits and so on. But this was also 2 years ago. We are much better than this now. So the intermediate summary is we have these bodies. We are working on them, right? We think that musculoskeletal robots are ideal and are even essential for meaningful interaction with the environment. They are a good basis for brain simulations, or for acquiring data for brain simulations, and for applying what we know about the brain using artificial controllers in robots, right? They are ideal for us as supporters of this metaphor of embodiment. And then, of course, we can add special features like variable stiffness, inherent compliance, and so on, right? But the problem is classical control algorithms are not available. They are not suited. They are not available. So we have to, if we have hope, because we're using what we know about the brain for controlling these bodies, but it's a long way to go. And of course, appropriate learning techniques are required, and that will be my last chapter in the last 5 or 10 minutes. What are we going to do about learning? Well, we are working on learning. Florian Walter, who's my PhD student, who unfortunately managed to come here, he is the head of this learning group, right? And we need the learning. But the problem is, what we have at the moment with all the deep learning and stuff is not enough for us. It's only a beginning. If you look at these deep convolutional networks, they're feed-forward networks. It's just not really the right match between the interaction, you know, where you have the perception, cognition, action loop, where you have an actuator. We need something that's how should I say, better than, or we need to advance the state of the art here to be able to make use of these technologies for robotics, right? While we see very good results in image classification and natural language processing with the you know, Siri and Cortana and all the stuff, I don't have to tell you, you're using it probably more than I do. The problem is really what can we do to control these bodies? And if we look at the brain, then we see the brain is obviously not just a you know, a one-way signal processor. There are lots of bottom-up and top-down connections, and also lateral connections between individual neurons, regions, and so on. And the question is, how can we profit from this insight to develop neural networks that can really control these complicated bodies in the complex environment that we want to live them in, right? And of course, we don't have the time, or we don't want to train the whole thing offline. We want to do the training and the learning online. So we put this thing in the room, and it should become better and better and better, right? So how do you do that? And again, the real-time interaction and the fact that you have a realistic physical body is absolutely essential for our work. And yeah, I mean, you're again more than welcome to help us here. And I mean, there have been some attempts to, you know, of course, other people are also working on this, but we claim that we, in this environment of the HBP, with the Spinnaker, for example, as a computing substrate, we have much better preconditions and a much better environment for for becoming successful than other people, in all modesty, again, right? So, yeah, so in other words, neurorobotics can do a lot for future machine learning. I think that, we think that the work we are doing here is central for the advancement of machine learning, at least as far as when it comes to controlling real machines in real time. Possibly, and this is a side aspect maybe for robotics, but it's a central aspect, so for example, for autonomous driving. If you want to really use such networks with their somehow possibly random behavior in a real technical system, then you would want to guarantee and to make sure that it always behaves the way you promise it to behave. Because if you have a car, for example, that you control with such a network inside, and in one out of a million instances or situations, it kills David, for example, then that would put an end to the development of Spinnaker. Who would want that? Right? So, in other words, that's only a side aspect here, but it's a central aspect, for example, if you want to use the machine learning or network technology, artificial network or brain technology in the automotive industry or in any industry, because people want somehow, not necessarily deterministic behavior, but controlled behavior. So these machines should be, their behavior should be under control, right? It should be predictable. Okay, let me give you an example here. So this is the classical video of a human, right? What a human can do, obviously. I mean, you could do that after some training, maybe. Well, I wouldn't probably not be able to. I mean, Dave, what would you think?
I'm contemplating the legal and ethical issue
Yes. Okay. Yes. Right. But here you can see this is the classical Ashimo video, right? I mean, it's actually a little bit longer. So compare the two, and obviously there's a lot to be done. So what we are doing here is we've been working on this. This is a one-dimensional a soft actuator which we control with a spinnaker board, right? In order to mimic the cerebellum as a proof of concept. So how does the cerebellum learn to match the desired trajectory with a real trajectory? And unfortunately, I'm already 1 minute behind schedule, so I should be quick. Just as an overview, we're using a model developed by the University of Granada, Eduardo Ros. I can't go into detail, but clearly this is a closed loop system. And if you look at the arm, so this is the set point over time, the profile that we want to. So we want to just to move it like a sine wave, and this is the actual movement in the beginning. We can look at all the signals in the cerebellum, like I showed you with the iCub. The end result is that, of course, the cerebellum is able to learn. This is also a very simple task. I don't know whether you really need 250,000 neurons for that, but again, here you have the spike train of some of where we put some needles in, some virtual needles, and then you can see over time that it really starts learning and that it then learns, right? So successfully. Again, this is a video, but it really works also in practice. Second example, and then I'm almost finished, so don't worry, is the so-called differential extrinsic plasticity. We're also working with Professor Deer from Leipzig University, who's been working on this for 25 years. So here the question is really how can we profit from the fact that we know that we are embodied and we have lots of sensors in our skin for controlling a robot system using all the external input, right? So I skip this. I also skip this. I only show you a short video here. So you can, let me put this off. So here you can see another soft arm, and this is trained by, so this is training by demonstration, right? So it has lots of sensors. It has a rather simple network inside, and it gets trained to follow the trajectory that it is shown. So here it is shown how to swing this bottle, and here there's why is this not running? Another example of the same system, right, that learns autonomously based on a rather abstract goal to swing this bottle, right? And here you can see also in both videos that a classical industrial robot with its dynamics would never be able to do that. I mean, it's just too far away in every sense. So this is a system with many degrees of freedom. It has a spherical joint. It is soft. It has it's highly nonlinear in every aspect, and it makes use of this nonlinearity because, as you can see here, the motion here is rather limited, and still it learns to swing the bottle with a large amplitude. Okay, future work, of course, extend, scale, and integrate everything across the whole hierarchy of things that I touched on in the last hour. Then, of course, incorporating further levels of this hierarchy, spinal cord, cortical models, and so on. And then also the scaling across time. What is the role of growth? What can we learn from the growth of creatures, humans, for ontogenetic, in inverted commas, neural development? What would happen if, I mean, you buy this robot in a store as I said before, you unpack it, you wanted to do something useful. But David's flat is probably much larger, bigger, luxurious than mine. Okay, so it would have to develop a probably completely different behavior, right, from from what it would have to develop in my, because I don't have many objects in my room. He has lots of objects in his room. So what would be a natural behavior that these robots would develop in his room as opposed to in my room? And these are the questions that are really relevant, because if you solve them, I mean, you can become rich. If you don't, well, maybe you shouldn't try. Okay, so we will build these integrated neurorobotic systems. We will make the neurorobotics platform to more and more people outside. Again, if you're interested, please get involved, right? We also have let me point you to the fact that we have a journal, which I'm the chief editor of in the Frontiers series, with very interesting articles, of course, only highly interesting. So go to the website. It's the only journal that is dedicated to neurorobotics exclusively. We have actually a surprisingly high impact factor already, if you're interested in this, which I would never expected. But because this is linked to Nature publishing, it's actually another achievement of Henry Markram's. This is a very good place to publish your papers if they get accepted. We also have, as I mentioned, we have good links with, in particular, the University of Tokyo, which I would consider the leading institution outside of Europe for this kind of work. We organized workshops and symposia, and we have what we call the HBP Neurorobotics Performance Show. Every 3 months we meet and everybody comes together. We show our latest results to each other, and it's always fun. And of course, if you are interested in coming, we can easily send you an invitation and you could join in. Right, so last slide. We will explore the possibility of reverse engineering the brain by building closed-loop robots. We will then contribute to becoming able to build interesting and capable robots for many, many domains, right, by providing modular bodies and modular brains. And of course, we want to build an open community, which you could become part of, to invite you again. So thank you very much for your attention, and I'm open for questions.